Today we are going to discuss about the Bragg's equation. Now let us start with the derivation of the Bragg's equation. Now let us first draw a diagram. Let theta be the incident angle of monochromatic X-rays of wavelength lambda with the parallel equidistant planes of atoms with interplanar spacing equal to small d. The waves are in phase before striking the planes. So these are light waves and these are parallel equidistant planes within a crystal lattice, and the waves are in phase before striking the plane, and theta is the incident angle. Now let us label two such waves which are in phase as wave 1 and wave 2. So let us use ink of another color. This is wave 1 and this is wave 2. So two such waves are labeled as wave 1 and wave 2 in the figure. After the reflection, the two waves will be in phase provided the extra distance traveled by wave 2 is an integral multiple of wavelength lambda. This is very simple concept. The extra distance traveled by wave number 2 should be integral multiple of lambda if it has to be in phase after reflection. It is very clear from this diagram that wave 2, which is represented as DEF, has to travel a little bit of extra distance compared to wave number 1. So it will be in phase if the extra distance traveled by wave number 2 is the integral multiple of the wavelength of that particular monochromatic rays. Now this extra distance can be evaluated. How we can evaluate the extra distance? This extra distance can be obtained by drawing perpendiculars to wave number 2 from V. So the perpendicular from B to wave number 2 will be like this, and like this. Let this is G and this one is H. So from the rule of geometry, this particular angle, that is GBE, should be theta, and HBE should also be theta. GBE should be theta and HBE should be theta. Drawing perpendiculars obtained by drawing perpendiculars BG and BH on to wave 2. So from this figure it is very much clear that AB is equal to DG and BC is equal to HF and GE is equal to EH is equal to D sin theta. No doubt about this, since BE is D. Look here, we have earlier we have declared that the parallel equidistant planes of atoms with perpendicular spacing equal to D. So therefore BE is equal to D and GE and EH is equal to D sin theta. Therefore now the extra distance traveled by wave 2 is given as DEF minus ABC. Very simple. From this diagram, the extra distance traveled by wave number 2 should be DEF minus ABC. So DEF can be represented as DG plus GE plus EH plus HF minus AB plus BC. ABC can be represented as AB plus BC. Since DG is equal to AB and BC is equal to HF, then it is HE plus EH. So this is equal to 2D sin theta. Thus in order to have wave number 1 and wave number 2 in phase, obviously after reflection we must have 2D sin theta is equal to n lambda, that is integral multiple of the wavelength of the radiation, where n is equal to 1, 2, 3, etc. So this is known as Bragg's equation. This equation is Bragg's equation. Here the constant n gives the order of the reflection. If n is 1, then it is first order. If n is 2, then it is second order. If n is 3, it is third order, and so on and so forth. Okay, so this is the derivation of Bragg's equation.